Hello everyone. In this part, we are going to go over developing a multi-layer perceptron model for rare event prediction. We will be building the model in TensorFlow 2, and as we saw in the previous part, in the last chapter, we will be using Google Colab here, the notebook in Google Colab, but you can do the same thing in your regular Jupyter notebook, on your local computer, on cloud, or any other IDE of your preference. Just because we are using Google Colab, we are going to do some traditional parts, which is connecting to the Google Drive so that I can read and write from my Google Drive directly. And we learned before that if you have Google Drive installed on your computer, all of these will be synced from your computer, so you can have the files on your local computer, which is synced on Google Drive, that you can read from here. Also, you can write here, which will go to Google Drive and eventually will be synced on your computer. We'll see that in today's lecture, that we will build the model by reading the data that is present in my local here, and due to which it is present on the Google Drive. And while we are building the model, when we have the result, we will plot the results and save the result on Google Drive, which will come on my local as well. We will go through all of this today. So, coming back to my notebook, I started with connecting to the Google Drive, some basic steps. It will take you to granting access page. There you will, when you grant the access, you'll get an access code. Copy the access code and put it here. It will let you mount or basically connect with the Google Drive. And then I do a step of changing my root path to my working directory so that reading and writing becomes easier. I can use a relative path. Again, we'll see all of these in the next steps. Then I always start with the basic ritual of loading the libraries first. Here you can see a few nuances, like I have mentioned our TensorFlow version to be 2x. This is again a Google Colab thing specifically because in Google environment you have multiple TensorFlow versions, at least at the time of writing this code. So you do want to mention that you want to use version 2, not version 1. So you start with importing TensorFlow, and then a bunch of other class of functions from TensorFlow mentioned here. Optimizers, model, sequential, and so on. Now, what I want you to look at is I also have some user-defined libraries. My user-defined library are present inside this directory utilities. Inside utilities, I have three files inside which I have some UDFs, some user-defined functions. I can import it like this by giving the directory structure in this manner. Utilities dot the file name inside it. This will load all the functions UDFs I have within data preprocessing. Then I load the data. In the last lecture we saw that if you do not have the data, you follow this link and get the data. I already have the data saved inside data directory here, which I am reading directly by giving a relative path and following some basic pre-processing steps to get the data ready. Now, the first thing I do as a part of pre-processing, as the next part of pre-processing, is shifting the data. We learned about curve shifting in one of the lecture parts, and here we are performing it. The functions for curve shifting is present inside my data preprocessing. Inside data preprocessing, I have a curve shift function, and because I have imported data preprocessing, I have access to this curve shift function, which I'm going to use here. I shifted y by 2 time units, which is equivalent to 4 minutes. I mean, which will be equivalent to building a model for 4 minute iteration here. Moving on, we do again some basic steps of dropping the time column because shifting has happened. After shifting, I can also validate whether shifting has happened appropriately or not. That's why I kept the date time column still. Now I can get rid of it when we need it downstream. And finally, I split my data frame into X and Y. Uh, Again, just drop the column Y and you have the X, and keep the column Y and you have the Y in this line. And then we are going to use the size of X, basically the number of features present in X in our modeling. So I am going to store it as a global variable and features. Now we have split the data into train, test, and validation sets. These are the basic steps for most model fitting process, so I'm not going to go deep into this. After splitting the data set, we will standardize or scale the data. Here I'm using a standard scaler. By the way, it is a good practice or an important practice to scale data before building any deep learning model, because deep learning models are complex. If we use unscaled data, the ranges of X can be different and model learning becomes difficult. So scaling is a necessary step when we are doing deep learning. Now, when we do scaling, we have different choices for scaler. Most popular ones are min-max scaler or standard scaler. We are using standard scaler here. Standard scaler transforms your original X, which can lie from minus infinity to plus infinity, into a Gaussian distribution with mean 0 and standard deviation 1. Here I mentioned the range of original X to be minus to plus infinity because in these cases it is good to use standard scalar and not min-max scalar. Min-max scalar is more suitable if the range of my X is finite. For example, in image problems, the X is a pixel, and these pixels can take a value between 0 to 255, which is a finite range. And if you have finite range, min-max scalar typically works better. But for our case, the values here is from, in this case, from 0 to plus infinity, which is still an infinite range. So we use standard scalar in this case. Another important thing you want to ensure is, and this goes for any type of modeling, is you should scale the data, build the scalar using the training data only, and then use that scalar to transform the rest of your sets, your validation set, your test set, and for any other rollout set. The reason is when we build the model, the information present in the training set should only be accessible during the model training. And data scaling is a part of model training. Had we used the test data as well during the scaling, that means we are using some information present in the test data in our model training or model learning. So we should avoid that. Because we should avoid that, we will keep the test valid or any other held out data set out of even the scaling process and use only the trained data. And that is why I first split the data into train, test, and validate sets, and then I'm doing the scaling here. Okay, now we are ready with our scaled data, I have the data split, I have the data shifted using curve shift function, and I have the data scaled. We are all good. We are all set to build my first MLP model, the baseline model.